Natan, hi.
Hi, how are you?
How are you? I'm good. Welcome to Devoxx.
Thank you so much. I'm really excited. It's my third year straight
I know
speaking.
that you are a very popular speaker at Devoxx and you speak at a lot of conferences. Have you ever counted how many Devoxx speeches did you have?
Specifically on Devoxx, it's my third time, and I'm really excited to talk today, both now and later on.
We are happy to have you. You can start your talk.
Okay, thank you very much. Okay, so welcome everyone. My name is Natan Silnitsky, and I'm a backend infrastructure developer at Wix.com. And this talk, you will see how you can create an event-driven distributed system comprised of various types of languages, including Java, Scala, Node.js, and Python, and have them all work seamlessly. And also this system is going to be fault tolerant, where you have every error handled and great resiliency, and also high performance, meaning that it allows you to process at high throughput and very low latency. And all of this is going to be implemented with Kafka, Kubernetes, and gRPC. So first, a few words about Wix. So it's a website building platform that allows you to manage your online business and presence. And we have more than 180 million registered users from more than 190 countries. And 5% of all internet websites run on Wix. So on our distributed system, we have more than 1,500 microservices. And when, for instance, a Wix user decides to publish their site, then a lot of different services are involved here. Of course, some editor service and meta site service, but also any application that is installed on the site, restaurant application service. So a lot of different services are involved in all kinds of flows, business flows at Wix. And most of our services are written in Scala and some Java, JVM, but there are also a lot of Node.js services and some Python services. And Wix processes more than 1.5 billion Kafka messages of business events, not analytics, every single day. So all of these microservices and high Kafka traffic means that we need the message flows to be performant and fault-tolerant and polyglot. And this is what this talk is going to show you how to do. So we're going to talk about event-driven programming. By the bedrock here is Kafka. And we have performance capabilities provided by Greyhound, which is a wrapper that Wix has created on top of the Kafka SDK. And fault tolerance will be achieved by using Greyhound and Kubernetes, different strategies of deployment and use of Kubernetes, and also how to achieve polyglot environment of multi-language environment, also by using Kubernetes and also gRPC. So we have in the past and also today have the request-reply classic communication style. So we have the ecom catalog service that wants to know whether the ecom app was installed on some site. So it will send an HTTP request over to the site apps service and get a response. So you can see here that these two services are highly coupled to one another, and that if the site app service becomes unavailable or something like that, then ecom catalog service immediately fails to do anything. And also the network could be unreliable and packets may be lost. So in that case, ecom will need to do some ad hoc retry to make sure that it can eventually get the response it needs. And of course, we're talking about flows here that can involve a lot of microservices, and handling cascading failures when you have 1,500 microservices in a very distributed environment can be very difficult. We want to have circuit breakers and automatic timeouts and all of that in order to achieve maybe a degraded performance when something happens, but definitely not downtime that our users will experience. So a great way to achieve this high availability and reliability is to introduce a message broker style of communication. So here we get a lot more availability and reliability by using a broker between our services, because it's part of a big clusters of brokers, and they also replicate all of the data that they ingest. So it's much more reliable. And now our services are completely decoupled from one another. They really don't care that anyone else exists. All they need to know is how to produce messages to the broker and consume messages from it. And specifically with Kafka Broker, we get much better performance than traditional message queues like RabbitMQ, because when you produce a message to a topic in Kafka, you actually produce it to specific partitions. That's what the topic is made of. And these partitions are just append-only logs. So just log files that continuously append new messages. So it's very fast and performant. And here you can see that Kafka Producer just appends a new message, one after the other at the end. And this could be later available in memory for the consumer. So it can consume really fast. And as long as it doesn't commit the message, it sequentially processes the messages, and it will commit the message only once it processes. So we know in this way that no message is going to be lost. And unlike with message queues that the message will be removed, here the retention can be infinite in the potential, although the default time that keeps messages is 1 week. And it's really easy to scale up the amount of messages we produce and consume. All we need to do is add more partitions to the topic, and then we have much bigger scale if we need to. Now, we created a Wix Greyhound, which wraps Kafka SDK both for producer and consumer. And the reason that we did that is we wanted to simplify the current Kafka SDK API and add all kinds of additional features that are required for our distributed system. And also, it provides an abstraction layer for our event-driven style of communication that all microservices use. And it's really easy to change stuff behind the scenes. Maybe we need to upgrade a Kafka version or fix some bug. And because all of these services have a head dependency on the library code, they can immediately get any update that we do seamlessly and automatically deploy it to production. So, and all of our services in production will get the updates really fast. So how do we achieve high performance? We're using extra high performance because we know Kafka gives us better performance than other traditional message queues. But let's see how we can get even better local performance with Greyhound. So here we have a schematic view of the Greyhound consumer, and the service provides and setups the Greyhound consumer with a message handler. This handler is basically a Lambda that just provides the code that will process the message. And Greyhound consumer out of the box gives us parallel message consumption. So it actually uses the Scala Zio library, which is a great library for high performance concurrent and asynchronous code. And it allows us to process messages in parallel, where each message will be processed on a fiber. A ZIO fiber is basically a lightweight thread where it has very low memory footprint, much lower than a JVM thread. And also context switching between fibers is really cheap. So the setup here is that for each partition that is assigned to this specific service instance, a ZIO queue, internal queue, will be created, and messages will be processed on this queue from each partition, because, as you remember, each partition is processed sequentially, and we'll have processing done in parallel for all of the partitions that are assigned to this service, each of them running on its own fiber. And when we want to achieve the maximum throughput allowed for our current Kafka setup, in this case, we have a topic, and it currently has 80 partitions. And we know that the message handler code just is mostly non-blocking I/O that uses the Netty gRPC client and has a response latency from the server side of 100 milliseconds. 100 milliseconds means that we can process 10 messages per second for each partitions. So 10 messages times 80 partitions gives us 800 messages per second. That's the maximum throughput that we can achieve with the amount of partitions that we have and the amount of time it takes to process messages on the server side of the message handler server call. Now, if we try to get there with a naive implementation using Kafka consumer, the regular Kafka consumer, then we're going to require 80 Kafka consumers, because when a Kafka consumer polls messages, it has to do that on its own thread. We cannot have multi-thread access to Kafka consumer API, meaning that we need to run 80 Kafka consumers with 80 Java threads if we want to achieve the maximal amount of throughput for this specific topic. But with Greyhound, we just set up a single Greyhound consumer, and it will run 80 fibers, because that's the amount of partitions that we get assigned to the single pod that we run in production. And as long as the Netty gRPC client manages to run 80 parallel non-blocking connections to the server side, we will be able to actually get to the goal of 800 messages per second processed by using only a single Greyhound consumer that's running very cheap fibers on a very small thread pool, because on our scenario, we don't really need a lot of CPU power, because it's basically just I/O operation. Great, so we gained higher performance by using fibers, and hopefully it will be out of the box in Java very soon with Project Loom and their virtual threads. Now let's discuss fault tolerance. So we want to make sure in our distributed system comprising 1,500 microservices that messages are not lost and eventually get processed successfully. And we achieve that with using Greyhound and also Kubernetes. So let's see how. We start off with a topic for renewing subscriptions, and then Greyhound consumer will consume messages and with the message handler that it is configured with. And we can also configure with Greyhound a retry policy, where if the message processing fails for some reason, there is a built-in retry producer that will produce the message to a retry topic. So the developer sets a back-off time in order to retry processing, and then on the message was produced to retry 0 after the failure, it will start the processing of the consumer side for that retry topic, after the backoff time that was configured. And if processing on the first retry topic fails, then of course we can have additional retry set up, and the built-in producer will produce the message to the second retry topic here, etc., etc. And mind you that with this type of flavor, messages can still be processed on the original topic. So all this design was inspired by an Uber blog post, and it is very popular at Wix in order to achieve consuming without any message being lost. And if we take a specific use case where we need to guarantee completion, we have here the Wix payment service that needs to renew subscription for site visitors that are subscribed to some service that a Wix user provides. So we have a job scheduler that knows when subscription expires and invokes the Wix payment service to start the subscription renewal process. So the Wix payment service will produce the message to Kafka Broker. So once the message is in Kafka Broker, we know that it will eventually be processed. Why? Because we have the ground consumer with the retry policy set up. So it keeps continuously retry until success. And even if a day passes and it still doesn't work because of some third-party issue or a payment provider or something like that, it doesn't really, it's not a big deal because we can put the message in a dead letter queue and then make sure that it is reviewed manually and decide what to do with it later on. Now, we have an issue here because we also having the flow of producing the messages to Kafka. What if currently the Kafka broker is unavailable? Well, maybe we need, maybe we won't be able to reach it and can't produce messages right now. So, and that can happen even on a clustered broker with high availability. This could happen. So what Greyhound does, it offers the resilient producer. So this producer first saves the messages to the local disk, and only then there's a fiber that will process these messages from the local disk and try to send them to Kafka. And if it fails, it will retry in the same manner that we have on the consumer retry side. Now, we switched over to Kubernetes a while back, and we saw that the resilient producer has some limitation here. Because on Kubernetes node, pods can be rescheduled and get away from this node or get crashed, and a new node, a new pod will be scheduled on a different node. And the most troubling part is that if a pod is killed, we don't have access to the volume mount that was mounted for this pod, that area, because the newly rescheduled pod will get a completely new volume mount from some disk on Kubernetes. So we may end up losing messages that remain on disk but have never been produced to Kafka. So how do we mitigate that with Kubernetes? So Kubernetes has different deployment strategies. There's the regular one where pods are scheduled randomly on nodes, and there's no coupling there whatsoever. But there's also the DaemonSet controller, where it deploys pods as a single pod instance for each of the Kubernetes nodes in the cluster that you configure. And that means that this pod is going to be available for all of the nodes in the cluster, and will be available also for other pods if they require it. So we created another service called Greyhound Scavenger that has access to all of the disk, local disk that is part of the Kubernetes node here. So when a pod produces a message to Kafka, but first saves it to disk, the scavenger can actually get access to this location where messages are saved. And if the pod goes down for some reason, the scavenger can notice that the pod is no longer available on the Kubernetes node, and then it goes and finds out if any messages are pending to be sent from the local disk that the pod used, and just does the flushing out for it and produces messages. So this way we have 100% guarantee that messages will eventually get produced to Kafka, even in case it is unavailable for some period of time. And also, it's important to note when you create pods that are controlled by the DaemonSet, it's important for them to be with a small footprint. Why? Because remember that with DaemonSet, this pod is going to be found on each and every Kubernetes node. So it takes up space that can otherwise be for pods from various domains in your distributed system. So the smaller memory footprint it takes and less CPU it takes, the more the Kubernetes node has to offer to other pods. Okay, great. And the third and final part of this talk is about how to achieve our event distributed system with multiple technological stacks of our microservices in a seamless manner. And we're going to do that and achieve that by using Kubernetes and gRPC. So at first, we just had JVM services using our Greyhound library. Once we started introducing Node.js services, it was obvious that we're going to need to have the equivalent solution for that technological stack. So the team in charge of the Node.js service infrastructure created Greynode and tried to get as many features that Greyhound has on the Node.js with JavaScript and TypeScript. So you can see here that code is actually duplicated in multiple languages, which is not an optimal thing to have. And also, Greynode needed to always catch up with the latest Greyhound features, and the Node.js infrastructure team wasn't always available to work on it because it was not their main task. So our Node.js services lacked features that were found on the JVM services. And also, the Greynode uses a library, Node.js library, that was not optimal for use with Kafka. It had problems of its own. So it was apparent that we want the Node.js services to actually use the Greyhound code, but it's a completely different technological stack. So the first attempt to try and solve this was to use GraalVM. So GraalVM is a runtime that allows to run JVM code and interop it with other languages, Node.js, Python. But the experiment here failed because it seems that GraalVM was not mature enough to have all of the code that needed to be run on Node.js actually work. There were a lot of interop issues. So this experiment failed. And the next try was to actually run the Greyhound code on a proxy service that the Node.js can actually call using gRPC. And the gRPC protocol meant that produce will be done from as a gRPC request from the Node.js service to the Greyhound proxy sidecar service. And when new messages were being consumed by Greyhound, they were actually sent as a gRPC request to a server that is implemented on the Node.js side. So we have bidirectional communication, client-server side on both ends of the Greyhound sidecar and the Node.js sidecar service. And because gRPC is actually built upon protocol based on protobuf, that means that we could have a strict interface definition language on the protobuf syntax that can be implemented both on the Scala side and on the JavaScript TypeScript side, and seamlessly be used by other languages as well, like Python, because protobuf has implementations for a whole host of languages. So no matter which language a Wix developer wants to use, they can actually just create the gRPC client and server and get it working for their needs quite easily. Now, our Greyhound proxy, I called it the sidecar. Why is that? Because it's actually found on the same Kubernetes pod alongside the Node.js application. So that's why I call it a sidecar, because it's found alongside it. So here we see a schematic view of the Kubernetes node. And we have multiple pods here. And here we see that the pod has not only the Node.js application, but it is deployed together with the Greyhound proxy sidecar. And they share volume mount between them for these two containers. So on a single Kubernetes node, we can have multiple pods having deployment of Node.js applications that automatically also have the Greyhound sidecar alongside them. Of course, Node.js applications can opt out and not get this attachment if they don't need Kafka at all. There is a memory issue for this kind of design because we have two applications instead of one in each pod, and also the JVM application has a bigger memory footprint than the Node.js application, just because of JVM itself and garbage collection, and also the netty part, gRPC, server, client, and keeping all the matrix that Prometheus needs to pull to get an overview of what's going on. So this really increases the cost of running Node.js microservices. So one way to mitigate this is to actually run the Greyhound proxy not in a sidecar container, but in a separate pod that is controlled by the DaemonSet, like I described earlier. So with the DaemonSet, we're going to have the Greyhound pod found as a single instance in each of the Kubernetes nodes that runs the Node.js applications. So we can have a lower memory footprint overhead because we have only one Greyhound proxy instead of a whole host of them. So let's do a quick comparison of doing a DaemonSet proxy or a sidecar proxy in Kubernetes. So with a sidecar, you get a much simpler design because you only need to handle state from one single Node.js applications on its consumers. But with a DaemonSet, you have a multi-tenant state where you need to keep track of all the various Node.js applications that go up and down. And also the lifecycle of the sidecar can be very, very simply implemented by just tracking the lifecycle of the Node.js application. If it goes down, when the sidecar goes down, and when they both get restarted and restart the protocol between them, so there won't be any state corruption inside the sidecar. Now, with DaemonSet, of course, it cannot mimic the lifecycle of the Node.js applications because there are a lot of them inside the Kubernetes node. And there's the bigger problem here that if DaemonSet pod goes down, for instance, on GA, then the Node.js apps can't produce and can't consume anything. So when there's a failure on the sidecar, it only affects the specific Node.js application. But then when there's a failure on the DaemonSet or restud on deployment or something like that, it affects all of the different consumers and producers that are required in all Node.js applications that come from various different domains. So it's a big impact potentially. But the big advantage of the DaemonSet, it has a lower cost and memory usage. So we can mitigate the Daemon Greyhound downtime impact by, instead of deploying the proxy as a DaemonSet, we can just deploy Greyhound producer as a proxy service, and not as a DaemonSet, just regular pods that are deployed across our data center, meaning that have high availability and they can always be available and no downtime for our Node.js requests. The downside here is that there is an additional network hop between different Kubernetes nodes, but because they are on the same data center, it's very insignificant, like a few milliseconds, and you can produce your message. So you can see here that we use Kubernetes flexibility to deploy Greyhound producers and consumers with different Kubernetes patterns, like DaemonSet and sidecar container, and we could also use StatefulSets in the future. So all of this is done to comply with the different requirements and needs we have to get the best trade-off between the performance we need, the easy code to write, and strong infrastructure to have in place with lower costs. And to wrap up everything, Wix has harnessed Kafka, Kubernetes, and gRPC alongside with our own custom infrastructure of Greyhound to achieve the Polyglot, fault-tolerant, easily scalable, and high-performant, event-driven distributed system. And I'm glad to announce that Greyhound is publicly available and open source. So you can check out both the Java and the Scala high-level API SDKs for your Kafka-based producers and consumers. And version 0.1 is out now, so you can check it out. So thank you very much. And if you want to get the slides from this presentation, then you can find them on SlideShare. I uploaded them up earlier. And you can also follow me on Medium and Twitter, to get updates on everything that my team is working on relating to Kafka, event-driven development, and all the stuff surrounding that. And if you want to check out previous talks I gave in conferences, you can find them on my website at natansil.com. So thanks again.
Natan, hi. Hi again.
Hi.
Thank you for a great presentation and a great talk. It was a pleasure to hear such a great presentation and preparation from you. And I know that you will have another talk later today. So
yes, that's right.
Wait for it. And we invite you and all our participants to join a Q&A session with you, because I'm sure that a lot of our participants has many questions to you after your talk. So welcome to Q&A session. And see you soon.
See you there. Thank you very much.
Thank you.